3, 2, 1. Let's see. Here we go. So continuing the design of my motor drive, I feel like there is too many loose ends now. There are so many pins that I haven't yet connected to the CPU, so I can't really make decisions on whether I would have enough pins to connect the switches directly to the microcontroller, or whether I need an I2C expander for any extra GPIOs. I think the most reasonable thing to do right now is to design the power supply, and then after that start connecting all the existing pins to the microcontroller, and then go back to both the EtherCAT interface and the GPIO interfaces as well. This video is going to be focused on adding the power supplies. I made a little note here for the chips that I found, which I would like to use for the power supplies. I think the TPS 54360 is a very cheap regulator that I've used before, which can support higher voltages, so I should be able to use it to convert 48 volts into 12 volts. Let's see here. So TPS 54360. This is a regulator that comes in a SOIC package. I think the proper way to pronounce the package name is SOIC, whereas I just say SOIC. I think that's just shorter. Let's see. So I'm going to pick this part, which is widely available in stock. 60 volt input. Let's see. Is there any? Okay, this is eco mode. This has eco mode. We don't really care about eco mode. I suppose that's the possibility to turn it off or save power in some other way. So I'm going to pick this more widely available chip, and I'm going to open the datasheet and look at the reference schematic. A good thing about datasheets is that they usually come with a reference schematic, so the amount of design work that one has to do and the amount of testing can be minimized. But it doesn't mean that we can just copy the reference schematic and just copy paste it and not do anything and not do any thinking when putting it into our schematic. It just means that this job is a lot easier than designing something completely from scratch. So let's see. Here's can I find the application? Typical application. Typical application. Is there any? Let's see. There is definitely a lot of information here, but what I'm interested in is the different possible ways of building a power supply from this regulator. And here is a typical application. 5 volts, 3.5 amps, and the input is 8.5 to 60 volts. Which is perfect for this motor controller. Input voltage. Let's see. So start input voltage is set to 8 volts, and it's set using these resistors on the enable pin. And probably the only thing we need to modify here is the feedback resistors here to get 12 volts on the output instead of 5 volts. The most annoying part about this regulator is that it needs to have like a compensation circuit with certain parts that I have to buy in as unit quantities because I'm never going to be probably using a 6.8 nanofarad capacitor anywhere else or 39 picofarads. That's just really obscure values, or 13K. So this little circuit it just means I need to add 3 more components to the bond list, which are ordered in unit quantities, which is a bit annoying. Maybe I should try a different regulator, but I'll do a quick search. I'm pretty sure that most probably I will use this regulator since I know it works and I've designed this circuit before. But I think it's still a good idea to see if there are any new products maybe, or if there is any other product that may be useful for us and doesn't cost too much. So I'm gonna go to power management ICs. I think these regulators come in the power management category. Switching regulators. Let's open this category and let's remove any filters. So can we get rid of the filters? Switching regulators. 19,000. That's better. Output voltage 12 volts. Because I'm going to be using this regulator to just convert from 48 to 12 volts. And I don't need to use it for any other supplies. It may be a good idea to just pick one regulator that has a fixed output set to 12 volts, and it will have fewer components necessary to make it work. So first and foremost, I'll look at something that outputs 12 volts fixed. So let's see, 12 volts. And oh, interesting. So actually I will go with one output. I was just thinking if there were 2 regulators in one package, I could have one for 12 volts and I could design another one, or have a package that has a 12 volt and a 5 volt. I don't know if there is any circuits that support that. Especially when it comes to fixed output voltages. I think it's better to just go with as generic search as possible, so that we get more products to choose from. Let's see. Output current. Output current. I think we need a bit of current there. Especially since this 12 volt output will also be connected to a plug that can connect to something else. There needs to be a possibility to draw more current than what the circuit uses. However, also even the circuit itself has certain parts that require rather large current consumption. For example, this chip draws 150 milliamps when everything is powered, or it draws a little bit over 100, but I put 150 here just so that I have a little bit of a margin there. And this one's actually run from the motor supply, so we don't need to care about this ones. But then we have buttons and we have LEDs, and just if we have a LED controller also, and all the LEDs happen to be powered at once. Which usually shouldn't be. It should be programmed so it doesn't happen. But if we have 8 LEDs and each one draws 20 milliamps, then we have 160 milliamps just for the LEDs. So the currents, they can add up, but I don't have anything here that goes beyond 1 amp. So I think a 3.5 amp regulator is probably a good choice, because it can also be reused for other things. So I can use the same IC for different applications as well. So 5 amps would be a bit of an overkill, and they get expensive when you get to higher currents. So let's see if let's not pick any specific current, but just sort by price. And perhaps by type. So boost converters are able to convert a lower voltage into a higher voltage, while buck converters convert a higher voltage into a lower voltage. We're only interested in buck conversion for this regulator, because we're not using, we're not going below 12 volts in supply voltage. So and input voltage max needs to be set to 60 volts, 60 or 76 volts. The good old LM2576. That is a nice regulator. Okay. LM2594. This regulator is the one you see in a lot of Chinese products. Although the Chinese modules, they don't use the high voltage version, so they go with the lower voltage version, which can only run up to 36 volts, if I can remember correctly. I'm going to check the datasheet for this one. And I'm going to look at the, well, yeah. So check this out. So this is, oh, is this, okay. It's only half an amp. So this is not, this is not really what I want. I want something at least, let's go for 3 or 9 amps. We only have 6 alternatives then. So for a fixed regulator, we only have a few alternatives. Yeah, it's basically just the LM2576. This one is not recommended for new designs. Low component count, step-down regulator. It's quite tempting, indeed, to use this chip. Maximum overline and load conditions. High efficiency. 63 volts maximum. .77% efficiency at 3 amps, 12 volts. Something that's interesting to look at also is how does it behave when the current is lower. Current limit. Typical characteristics. Okay. Situation. Let's see. So we're going to be running it at, let's say, 50 volts. And how much does this operate on? What is the switching frequency of this one? This one is 2 megahertz. What I'm interested to know here is what happens if the voltage on the input suddenly rises and the regulator has and the regulator is in the middle of one cycle. Will it automatically adjust the cycle on the fly, or will it momentarily output more voltage on the output? They rarely tell this in the data sheets. Like what does the output look like if the input is a variable voltage, which it will be in this case because we have a motor connected. So the voltage on the input is going to rise and fall. So it's going to rise and fall basically to the nominal supply voltage, but it can definitely rise, and it's interesting to know how does this regulator respond to such a rise. Delayed startup. Fixed output voltage version. $15 volts. Okay. Right, so we can pick the inductor here. maximum load current. So okay, so this would be, if I were to use a fixed version, it would be this one, HV12. So it looks like I can only reach if I want to get, let's see, the maximum load current is between 1 amp and or something, somewhere around, like, let's see, so 15, so 600 milliamps if we use this one, if we use this inductor, if we're gonna get 2.5 amps at 50 volts. So when looking at this data sheet, it becomes quite apparent that this regulator is going to behave differently depending on load conditions and input voltages, which is not the case with the other regulator. This regulator is much more is much better designed and less sensitive to changes in the load. Let's see. Can we get some graphs here? Where did they put there? Let's see. Could this be typical characteristics? Okay. So soft start time, high side MOSFET. This diagram says, this diagram describes how the resistance of the output MOSFET rises with temperature. When a component gets hot, it's actually easier for it to get even hotter because the resistance rises as the temperature rises. And when the resistance rises, it creates more friction, and so the temperature rises even more, until the component reaches kind of an equilibrium point where it cannot heat up more, or where it can dissipate all the heat, because also the dissipation I think it rises exponentially as the temperature rises, or like the how much temperature the component how much energy the component dissipates. Switching frequency versus feedback, supply current, input voltage, put SV, 6-12 step down regulator with an integrated high side and channel MOSFET. The device implements constant frequency current mode control, which reduces output capacitance and simplifies external frequency compensation. The wide switching frequency range from 100 kHz to 2.5 MHz allows either efficiency or size optimization when selecting the output filter components. The switching frequency is adjusted using a resistor to ground. Okay. Okay, this is the most boring video so far. I'm going to stop this video and I'm going to go back to